I'd like to welcome to the stage Sam Skillman, and Sam is from Descartes Labs. He leads the engineering teams in building a cloud-based platform combining petascale Earth observation data with machine learning techniques. And so the goal is to model the world, which is a pretty audacious goal. I want to welcome Sam. Please share. Thank you very much.
Thanks.
Enjoy.
Afternoon, thanks for having me. Hope your lunches are going well so far. So I'm going to talk a little bit today about the intersection between high performance computing, cloud technologies, and how a company like ours can kind of exist out of nothing, having no previous hardware of our own. So I'm Sam Skillman. I head up the engineering team at Descartes Labs. Quick bit about myself. My past life was in astrophysics. I was a DOE computational science graduate fellowship at University of Colorado in Boulder. Focused a lot on large-scale, high-performance computing. One of the last projects that I was involved with was when I was a postdoc at Stanford. We were running a trillion particle cosmology simulation. There's a slab here of the dark matter density of one of these trillion particle simulations. One of my favorite kind of party tricks is pointing out that the data from one of these simulations is just sitting on a web server. So if you want to all go to darksky.slack.stanford.edu and click on that 31 terabyte file, that would be great. So Descartes Labs formed in about 2015. Actually formed just about 5 years ago. I joined in March of 2015. This is the team. We're now up to about 110 people. I just put this slide together and it was kind of blowing my mind because this is essentially the progression of the company over the last 5 years. The top left being the original founding team, bottom left 2016, middle top 2017, 2018 on the top right, and then we just had an all hands meeting just about a month ago in Santa Fe. So the founding team came out of Los Alamos with a large amount of experience in large-scale computing, remote sensing, machine learning, astrophysics, cosmology. It's a whole hodgepodge of folks. And what the founding team was realizing was that the combination of the availability of very large-scale remote sensing data sets with cloud computing could enable a company to form and start to answer questions about how the Earth is changing and how to kind of find, monitor, and predict everything that's happening. So that's what the company does. We pull in tens of terabytes of data every day from public satellite constellations, commercial satellite constellations, weather data, other sensor data from everything from ships to really anything else that sends off a geolocated point. We pull in that data, we kind of massage it, clean it up, make it so that somebody who doesn't have a remote sensing background can work with this data in more of a data science approach as opposed to having to have all this knowledge about what each of these sensors are, what they might mean for some particular application area. That allows you to then model whatever problem you may be working on, combine it with potentially ground truth data from your own company or your application area, simulate the phenomena that you're interested in tracking, and use that to drive decisions within your business. So that's what we call our data refinery, and we work with large companies, monitoring and tracking really anything that you can see from space or other sensors. So I want to talk a little about the origin story of our company because that's really one of the key points here. And that was to look at crop production across the US. So where and how well is corn or soybeans growing within the US? What's that final production going to be? That's interesting to lots of different types of people, including governments knowing whether or not there's enough corn or food to feed people. It's interesting to commodity traders who want to predict the supply and demand balance for these commodities. And to do that, we wanted to make use of kind of a new asset that became available. previously, a lot of remote sensing data, satellite imagery, it was really available through FTP servers from various government organizations or private providers, but it wasn't available in a very high bandwidth capacity. In kind of 2014, 2015, some of this data started being put on the hyperscale cloud vendors. So both Amazon and Google have started adopting some of these open data sets. So around 2015, at this point, there was about a petabyte of Earth observation data available in the public cloud. We supplemented that with some of the data that we had to pull from those FTP servers in a laborious way over months at a time. But you add it all up, and there's about a petabyte of data there. What we needed to do next was kind of pre-process all of that data to make it amenable to be input into a machine learning model. And so one of the goals here was to process this very large-scale data set as quickly as possible in order to then enable the applications that would come later. So on April 15th, 2015, we spun up about 30,000 virtual CPUs on Google Cloud. We didn't sleep much because we were monitoring this because we had never done something at this scale before. We processed all of that petabyte of data using our preemptible VMs over these 16 hours, where if you look at the kind of time in the bottom left chart, time is on the x-axis, the amount of data processed into the system is on the y-axis. You can see that we've pulled in about a petabyte of compressed data, which comprises about 3 petabytes of uncompressed data, and stored that back in our cloud storage system in JPEG 2000, which is compressed down to about 200 terabytes or so. The graph on the bottom right is the network bandwidth, showing this very real application pulling in 23 gigabytes a second of data into this distributed 30,000 cores and processing away on it. To our knowledge, this is the first time that a petabyte of kind of natural physical data has been processed in under a day. And the output of that was a set of data that we could then put into our machine learning models, where we could both run operations like identifying, for every given pixel on the Earth, what type of crop that is, and then ascribing a yield to each of those pixels. How many, for example, bushels per acre is that pixel going to produce by the end of the season? And you can use this to then predict those final numbers and kind of give a prediction ahead of what you would normally get from, for example, the USDA. So at this point, we're a company of about probably 10 or 11 people at this point. We didn't have a single server of our own. We have a number of laptops, a couple routers to get online, but no actual physical servers. So what that allowed us to have is this very crystal clear product focus on what we wanted to deliver. This came out, we had an article in Bloomberg about predicting how much corn there was going to be, predicting that there was going to be less. This actually ends up moving the corn commodity market in a significant way, and we've been kind of off to the races ever since. So we've got zero upfront cost at this point. Our computational footprint, it fluctuates anywhere from tens of cores to tens of thousands of cores. And that's all just completely elastic and tunable to us depending on what application we're working on at the time. So that allows us to do a progression of applications. One of the next applications after this corn production was creating what would be a cloud-free view of the Earth from a multi-year archive of satellite imagery. So on the left is from the USGS Landsat 8 satellite. The middle one is a radar system called synthetic aperture radar from the European Space Agency. And Sentinel-2 is another multispectral satellite similar to Landsat. And so for each of these operations, we're going through the entire archive of multiple years of satellite imagery, picking out the most cloud-free summer-like day, because even if the clouds are gone, there's still going to be snow in the mountains or things like that. So we try to pick particularly sunny day and then create this composite. And you can go to maps.descarteslabs.com and you can browse around these composites. This is processing, on the left, 320 terabytes of data input. In the middle, about 86 terabytes, and on the right, 120 terabytes. All of this, again, just scaling up within the Google Cloud ecosystem. On top of that now cloud-free mosaic, we can start to build additional applications. An early one in, I think, 2016 is called GeoVisual Search, where we take one of those composites, we then chunk up the trillions of pixels into little 256 pixel chunks. And for those billions of small images that tile the Earth, extract a visual feature vector. We essentially take something like ResNet, chop off the last few layers of that deep neural net, creates an abstract feature set, which we can then use for a proxy for the content. You take something like 512 features in this 512 dimensional space, and then for every potential image that you click on, you can find the most visually similar pieces from around the Earth. And so that can be done either doing a direct search where we're dropping down into running with particular intrinsics that are tuned for the Intel CPUs that we're running on, or you can use locality sensitive hashing to do faster lookups. But what that allows you to do is, for example, click on Mile High Stadium just a few blocks away from here. And on the left, you'll see all of the things that also look like football stadiums on the left. So you can do this. It's a fun tool. If you go to search.descarteslabs.com, you can play around with it yourself. But you can start to build a visual index of the Earth, which then allows you to do that find part of our processing where we're looking for all the objects that we might be interested in. So out of that, we continue to expand our footprint into Google Cloud and take advantage of additional systems there. We were the AI Partner of the Year in 2018, and this kind of just allows us to, instead of building out some of these specific database backends, et cetera, we can start to pull together different applications and actually just focus on what our actual problem is, what product that we're building. So a lot of this is pointing and talking around some of the economics that are involved with cloud computing. So in 2016, we wrote a paper, and this table describes the fundamental costs of compute and I/O in kind of cloud ecosystems. And so the left is in dollars per second is kind of the unit here. So whether you're talking about gigabytes stored of cloud storage, or Linpack floating point operations, or pushing bytes to the public internet, it's all described here. And so, for example, storing a petabyte of data for a year costs $315,000. But a single dollar can buy about 60 seconds of a skilled software engineer. It can move 10 gigabytes of data to the public internet, or it could provide 6 petaflops of compute operations, right? So that starts to tell you that, the balance of the fundamental costs associated with building some product are pretty crazy, because the same 60 seconds that you pay somebody to be working on something, maybe writing a little bit of code, in that same amount of time, you could be, or for that same cost, you could deploy, a petaflop of operations. Really tells you what you have to get people to be able to do in order to be worth their hourly wage, essentially. On the other side, at the larger scale, there's incredible movements from the kind of procurement side of this in cloud data centers. If you look at the top here, this is the Intel revenue from up to 2018, showing that the data-centric revenue, which is the second line, the DCG line, was up about 20% year over year in 2018. On the other side, you have somebody like Google and Google Cloud spending $25 billion on CapEx in 2018 compared to 12 billion years just the year before. So these two things are related, right? The amount of compute being deployed at these hyperscale cloud vendors, it dwarfs a lot of the on-prem deployments that you could think about, and really tells you that the demand for new features, new types of chips, are going to be heavily driven by these cloud vendors themselves. They're going to be saying, what type of new processor does Intel need to produce to satisfy their customer needs? All of this is great for us because it means that we can do things cheaper, faster, and iterate more. So that same pre-processing of a petabyte of satellite imagery in April 2015 cost about 10,000 bucks. By September 2016, this could be running on preemptible nodes. It's down to about $3,600. With the introduction of Skylake processors, we actually saw performance boost in specifically areas where we're either decompressing or compressing this imagery, which allowed us to drop down that fundamental cost even more. So we didn't have to go out and buy a new data center of Skylake processors. It was another option to click in the cloud configuration UI. So we got access to Skylake on Google Cloud in February 2017. This was about 6 months before it appeared in large-scale DOE compute facilities. That means we can evaluate and test that technology and decide whether or not we want to adopt it very early on, right? Similarly, earlier this year, they started introducing these memory optimized VMs. This is using all of the things like Optane for very large scale, large memory footprints. I mean, when I think back to being a grad student, the idea that I could get access to something like 400 cores and 11 terabytes of RAM was kind of mind-blowing. Like, I had to write tons of grants, go through a very long process to get access to one of the few national supercomputer centers that would have something like this. This was 8 years ago or so. And now you can just swipe a credit card, right? And so, yes, it costs money, but the access to that is instantaneous. That also allows you to move between different scales. So most of our lives, I'm starting to call this like the inside baseball of computing, because it really only matters to a lot of the folks in this room and at this conference this year. So we spend most of our time down at the bottom left, where we're editing software. We're focused on one task. It's maybe using one core, run your VS Code or something. You might be developing software where by that I mean there's some testing and integration going on where you're maybe using up to a node or something like that, or you're doing a small scale test. Maybe you're running continuous integration where now you can blast out to lots of tasks and accomplish things, even though each one of those individual tasks only takes a single core. And maybe somewhere in the middle, you're training an ML model across a couple nodes, but you can do this across thousands of tasks running. It's really the outfield out here, which takes really a tremendous amount of effort that is rarely done by any individual, right? Whether it's a Gordon Bell Prize winning project or deploying web services at the millions of concurrency server response rate, right? You might be doing that same code from a Gordon Bell project, but then running it operationally and running over many instances of those. But to push out there takes an incredible amount of work. And one thing that you start to gain by having access to cloud is the ability to move between these things very rapidly. You may not be able to get the Gordon Bell scale compute, but a lot of these other bits. For example, again, just like getting that high memory large node on Google with a credit card, you can also procure essentially more HPC performance in terms of Linpack performance as the Roadrunner supercomputer in Los Alamos in the early 2000s. And that was a $200 million-ish project. So we decided to actually do this. So earlier this year, we spun up 40,000 cores on AWS, and we ran Linpack. And we got 1.92 petaflops, put us on the top 500, which is kind of strange because we don't own that system. We wrote some of the software and tuned Linpack to run on this thing. To our knowledge, it's the first time that it's been run on a virtualized public cloud resource, and it costs about $5,000. So we then shut it down, and we never look at that again, right? So it's an interesting opportunity to think about. We heard about bursting to the cloud for computational resources, and even for tightly coupled MPI processing, that's actually possible now. Again, the ability to get access to different hardware. On the right, I opened this up last week or so, and it's like, okay, I would like a Cascade Lake, 80 cores, 640 gigabytes of memory. Click to deploy, right? That's democratized access to new hardware. On the left, I've got a Skylake system, about 100 cores, 96 cores, and 8 NVIDIA Tesla V100s, right? Click to deploy. So you can just move around in this parameter space of how much compute, I/O, et cetera, you want, and optimize it for what you need to get done. For us, a lot of that looks like data-intensive workloads. We're pulling in a petabyte of data, so we need high-performance file systems, effectively, to work with. So one thing that we deployed was a Fuse-based file system that allows us to access objects stored in Google Cloud Storage through what looks like a POSIX interface. And we scale this out on a number of nodes, and we can actually scale this up to about 380 gigabytes a second of read bandwidth coming out of cloud storage, right? So now if you're running these very large-scale distributed inference models, for example, you can do that by still using the same software that is expecting a POSIX I/O interface. One thing that you'll see here, the open latency for these files isn't super short, right? This is tens of milliseconds, which means that you maybe don't want to do all of your work with very tiny files, for example, but you don't usually want to do that anyways in large-scale processing. So out of that opens up possibilities. For example, we mapped all of the buildings in North and South Carolina prior to Hurricane Florence overnight. So hurricane was coming in. It's like, okay, let's map out all the buildings. Can then use this downstream to look at, where was there damage to these homes or buildings? What was the, long-term effects of the layout there. And it's not just us that are doing this, of course. This was particularly interesting to me with my astrophysics background. Earlier this year, the Event Horizon Telescope put out directly imaged the event horizon at the center of our galaxy. What I didn't really realize at the time was that part of that data analysis pipeline that they used to do that was actually using effectively cloud storage and cloud technologies. They had access to a research system at TAC in Indiana to test out some cloud-based data analysis, which they then ported over to Google Cloud, where they actually ran the production run. There's a couple different reasons why they did this. One was that the scalable data access and bandwidth coming out of cloud storage was just beyond what you can normally get easily through other systems. It was also much easier for them to share their analysis around the globe, where this was a global collaboration across a number of institutions. Having access through that and having that data gravity of having it all there enabled this team to do that. So because this prototype worked really well, they actually applied to NSF and got a grant to deploy this on Google Cloud. So I think this is a really interesting case of actually transforming some of these very large-scale science programs dealing with very large data sets to commercial cloud instances. So for us, when we look forward, we're looking at essentially the effects of data network effects. So this graph is, as a function of time, how much data is stored in our data platform. And each line is a new satellite that's been launched, or a constellation of satellites. Sometimes you have like large swarms of the same type of satellite. And what this means is that the richness of each additional data set is not limited to just its own use case. It's a combination across all of these data sets. So the next few slides kind of just go through the different types of satellite data sets and their applications. This is showing an area where there's a fair amount of vegetation from 4 different satellite sources. So Sentinel-2, Sentinel-1, Landsat 8, and high-resolution Airbus Pleiades data. So some of these can be used for vegetation analysis. Synthetic aperture radar from Sentinel-1 can start to look at textures of the ground and how that changes. You can create derived ratios that may point to what type of soil is around that area. And then the final one is a high-res look where you actually see a network of oil platforms, like drilling platforms. This is, again, Sentinel-2 looking at the health and vegetation in Ukraine, looking at these really beautiful kind of patterns that come out of the crops that get planted there. At a very large scale, you start to look at things like the Permian Basin in southeastern New Mexico and northwestern Texas. And this is showing just like a vast network of both agricultural fields and all of these oil rig platforms. So you can start to monitor like, oh, there's a new rig showing up here. There's new exploration happening here. And start to predict what that's going to mean for global supply. This is a hyperspectral or multispectral view of Santa Fe, New Mexico. I like this one because it looks like the golf courses here are made out of gold. Those are the little tracks around the outside of the town. This is showing the normalized difference in the water index. So bright areas in yellow show very high density of water because you have to water those golf courses very heavily. This is a very large scale. This is coming in from GOES-16, which is a weather satellite that takes an image of the entire full disk of the Earth every half hour, and it shows up in cloud storage just seconds later. It's pretty incredible to me. The fastest one I saw was something like 10 seconds from the time it was acquired on the satellite in geostationary orbit to the time when it hit cloud storage and could be analyzed, right? And so this is being used to monitor, of course, hurricane seasons, different atmospherics, pollution, et cetera. In the bottom left, it's just out of view, but there's a tropical storm down there. And down in in South America, there's actually the eclipse from earlier this year. This is Tokyo Bay in synthetic aperture radar, where the benefit of synthetic aperture radar is it's actually not relying on the Earth's or the sun's radiation to reflect back up to a sensor. It's actually beaming down 5 gigahertz or 5 centimeter radiation to the Earth, it bounces back up and it's an active sensor. It's actually quite good at picking out things like ships, and so you're seeing all the ship traffic happening in Tokyo Bay. You can start to categorize and locate these ships from satellite imagery, match those up with things like the AIS data streams that the ships ping out to not run into each other. You can also use this to track ships where they shouldn't be, for example, in marine protected areas. The synthetic aperture radar actually penetrates clouds, so it doesn't get affected by that, which all of the normal, like Landsat 8, MODIS, Sentinel, all just get obscured. In California, this is near Redding. This is from a fire within the last year. You can start to monitor both the status of a fire as well as the kind of burned area from within it. This is the visual view. In a second, I'll switch over to the shortwave infrared view. We've actually got a production pipeline running, which is using the GOES satellite just a few slides ago at that very large scale to monitor for places on the Earth where it is much hotter than it used to be or should be. And that's a very early warning trigger of where there might be a fire starting. That feed is actually getting sent to agencies in California, also the LA Times, and that showed up in a article just a few weeks ago. But you can start to see the visual bands here. And if you look at the shortwave infrared, you can actually see the progression of the boundary of that fire. So you can start to track which areas were burned, which areas are in danger coming up next. This is not a very high revisit rate satellite image, so it's mostly useful for post facto analysis. But still, it allows you to gain insight into the dynamics of that fire as well. A recent satellite was launched by a European Space Agency called Sentinel 5P. On it, it's specifically built to monitor greenhouse gases. And so this is a global composite from earlier this year that looks at nitrogen dioxide, where you can see essentially cities lighting up as NO2 is being emitted. It's a tracer of other greenhouse gases. In Africa, you can see the effects of what we think are just the annual fires that burn that release this emission just from burning out those grasslands. One of the most interesting pieces that popped out to me was actually the shipping lanes that you see in Southeast Asia, where the individual ship might not emit enough, but if you composite this over time, you start to see the tracking of those shipping lanes. So all that is to say that we can kind of combine those pieces and use them for the applications that matter to our customers and to our users. So for example, we can deploy a machine learning-based building model that here is looking at the San Francisco Bay Area. We can start to look at trees, which is kind of an interesting one. Trees are interesting not just because they are nice indicators of healthy landscape, but you can take something and debug it on this local scale, identify where these trees are, and then immediately scale out your resources and deploy it globally. So now you can look at kind of the structure and location of where trees grow and don't grow around the world. One of the possible use cases here is using this as indicators for economic prosperity. Very nice tree-laden streets are usually indicators of affluent areas, for example, and you can start to monitor how that changes in cities over time as populations grow and diminish. So I want to leave with just some parting thoughts here, and it's really comes to the heart of why a company like ours can exist out of nothing. There's a number of instances where major advances in computing have been driven by commodity hardware and commodity resources. So for example, commodity PCs leading to the start of Beowulf clusters to the point where today every top 500 supercomputer is running Linux, which I think that full 500 started just a year or so ago. You have things like PlayStation 3 leading to the Roadrunner supercomputer where the first petaflop is achieved. You have web-scale deep learning applications where the first EXA-ops are being conducted at national laboratories now. That also means that you have just tremendous choice on where and how to deploy your software, and you're no longer limited by the capital expenses that you may have otherwise had to work with. It allows you to completely focus on the product that you're building. So you can spin up on-demand HPC resources, get a petaflop for 5K if you are so inclined. You can have very large-scale, on-demand, data-intensive science applications. You can spin up and spin down, remove all the limitations that would normally come from building out for your peak load, right? And instead just focus on your time to solution. And finally, one of the other huge benefits for us is that it allows us as a small startup company to leverage leading edge technology from, for example, Intel, where we can pick, I would like a Cascade Lake processor now, and I would like 1,000 nodes of that, please. Does it work? Yes. OK, let's adopt it more. Let's scale out further. But I don't have to pay those upfront costs to be locked into that yet. And that just allows just a completely different scale of fast iteration and overall time to launch. So thank you for having me and listening to me through your hopefully delicious lunch. And thank you to Intel organizers, and have a great week. Thanks.